Good morning, Algebra 1 CP students. Hopefully you're having a great day so far. Today, I'd like to take our inequality conversation one step further and discuss with you compound inequalities. Compound inequalities are pretty much when we have two inequalities going on at the same time in the same problem. All right. Our problem solving processes for these really aren't any different than when we solve just regular old inequalities. We're just going to solve each of these separately. However, when we're representing our solutions on a number line, we have to be mindful of the fact that we're going to account for both inequalities simultaneously. So the solving is going to be very similar, the graphing is going to be a little different. There are two types of compound inequalities. There are things called disjunctions that involve the word or. That's what we're going to talk about today. And there are other things called conjunctions, like conjunction junction, that involves the word and. Props to you if you get that reference. Today we're just going to focus on the or case, and tomorrow we'll discuss the and case. So talking about the word or, it's important, I think, to think about what the word or means. If I told you that I'd be happy with one thing or another thing, well then as long as I receive one of those two particular cases, then I'd be satisfied, right? And a math problem works very similarly. For this scenario, what this is essentially saying is we want to find a value for x such that if I did x plus negative 1, I would have a value that's greater than or equal to 9. Or this scenario would also be satisfied by a value for x such that that number divided by 8 would be less than 1. All right? So as long as we can make one of these two cases true, then my problem would be satisfied. If we can make them both true, that's even better. That doesn't always work out in every problem, but we'll see that in a little bit. So what I'm going to do in order to tackle this is I'm really just going to solve each thing separately and try to represent them together on the same number line. Take a look. This first one's just a one-step inequality. Sorry for the little scribble here. It's supposed to be an x. I would add 1 on both sides in order to solve it, and we just get that x is greater than or equal to 10. Okay? This inequality is also one step. I would just multiply by 8 to undo the division by 8 here, and I'd get the solution of x is less than 8. Okay? So what this inequality is suggesting that if my value for x is greater than or equal to 10, I'd be happy. Or if my value for x is less than 8, I'd also be happy. So we can represent those solutions simultaneously on a number line here. I'm going to try to be as neat about this as possible. I'll say that if this is 10, then this would be 9 and this would be 8. I encourage you to try to draw an accurate graph if possible. And I'm satisfied by all x values that are greater than or equal to 10. So I'm going to shade in 10. And just graph that idea, right? Those are all my x values greater than or equal to 10. But this solution set also includes all the values for x that would be less than 8. So I'm going to put an open circle on 8 because I'm not including that. And I'm going to shade to the left of that as well. All right. So really, the only values for x that are not fitting for this type of a problem are those that fall within this range in the middle. Everything else is totally fine. If we're greater than or equal to 10 or less than 8, we're in the clear. All right? So really, it involves just solving both inequalities simultaneously and then graphing their solution on a number line. All right? Let's take a look at another problem in which the inequality is a bit more complicated to solve than that. Okay? How about something like this? We have 10x plus 4 is less than negative 6. So I'd be happy if I can find x that falls in that range, or I'd be happy if I can find an x that falls in this range, where 7 minus 6x is less than or equal to negative 53. Okay. So let's try to solve these inequalities. We're just going to, again, treat them separately. We should be very comfortable solving a two-step inequality at this point. Same thing over here, two-step inequality. I would, of course, get x alone. In order to get x alone, I would subtract 4 from both sides, which would give me that 10x is less than negative 6 minus 4, negative 10. And then I would divide both sides by 10 to undo the multiplication by 10. And we'd end up with the fact that x is less than negative 1. Okay, no need to do any flipping with the inequality there. We just divide it by a positive number. Okay, so I'd be happy if my value for x is less than negative 1. Or I'd be happy if we can make this happen. If I would subtract 7 from both sides, get that 6x is less than or equal to negative 60. Sorry, negative 6x. negative 6x less than or equal to negative 60. Divide both sides by negative 6. And notice we are, in fact, dividing by a negative, so I am going to flip-flop that inequality and get that x is greater than or equal to negative 60 divided by negative 6, positive 10. So, for a graph of this particular problem, my value for x would be satisfied if we are less than negative 1 or greater than or equal to 10. What that'll look like on a number line is the following. Okay? You do not have to label these exactly, but I would encourage you to try to be neat with your number line graphs. If I'm going to say that negative 1 is down here, right? 10 would probably be somewhere up here. It would be pretty far away from negative 1, right? But I'd be happy with this if my x value is less than negative 1, which means we're going to include all that stuff on my graph. And I'd also be happy for all the x values greater than or equal to, so that's why I'm shading in the circle there, greater than or equal to positive 10. Okay? So our graph would look somewhat like that. All right, these values, I would not be happy with those because those don't satisfy either of these conditions. But as long as this is true or this is true, we're good. All right, let's see one more that kind of works itself out that same way. Something like this. If I have, we'll use some variables on both sides this time. Should be a nice review. 4x minus 3 is greater than 3x minus 7. Or negative 3 times 1 minus 2x is greater than 4 plus 7x. Okay? Let's try to tackle a problem like that. We want to find out a value for x that satisfies either this case or this case. So let's just solve both of them separately and then graph them together on a number line. Notice that's pretty much what we're doing. It's almost like we took two inequality problems and just put them together, right? So in order to deal with this, I would probably elect to subtract 3x from both sides in order to eliminate the 3x here, right? Move all the variables to one side. It gives us 4x minus 3x is 1x minus 3 is greater than negative 7. And lastly, to get x alone, I would just add 3 to both sides. And I would say here that x is greater than negative 4. Okay? So that's our first condition. Let's deal with our second one now. We have a little bit of distributing to do here. That gives us negative 3 times 1. Negative 3 times negative 2x plus 6x is greater than 4 plus 7x, like so. I'd now want to get all those variables on the same side. I'm going to subtract 7x just to move everything over to the left. It gives us negative 3 minus 1x, minus x, is greater than 4, right? 6x minus 7x would be negative 1x. Couple more steps to go. We would add 3 to both sides to isolate negative 1x being greater than 7. And lastly, to get rid of that negative 1 times x, we divide both sides by negative 1, which is going to cause that inequality sign to flip, giving us that x is less than negative 7. So this inequality states that we'd be happy if x is greater than negative 4 or if x were less than negative 7. So putting those on a number line would look like this. Here we have negative 4. Here we have negative 7, right? I'd say x is greater than negative 4, open circle, and shade to the right. Or x is less than 7, open circle, and shade to the left. Okay? So hopefully that makes sense. Again, it's really just doing two inequality problems at the same time. All right? Now the question is, does that mean that for every problem where we see the word or, you're always going to end up with the inequalities going in opposite directions? Like you're always going to end up with one going this way and one going this way. No, that is not what that means. We can have it where both of the inequalities just so happen to go in the same direction. What does that look like? Well, let's take a look and find out. Okay, let's find out. Consider something like this. We'll keep it a simple inequality first, and then we'll do one a little more complicated. If I had negative 6x is less than or equal to negative 42, or x divided by 5 is greater than 2. Okay, consider something like that. Well, in order to solve both of these, we're still going to solve them both. I would, first one, they're both one step. Divide both sides by negative 6. We do have to flip that inequality because we divided by a negative. I would get x is greater than or equal to negative 42 divided by negative 6, positive 7. Or on this side, I'd have to multiply both sides by 5 to undo this division by 5. And we get that x is greater than 10. All right. So take a look at what this would look like on a number line. Do you notice like x is greater than, like they're both kind of greater? So what this is going to look like on a number line, right? Let's graph the x is greater than 10 first. X is greater than 10, suppose 10 is here. I would have my open circle, and I would be shading to the right for everything that's bigger than 10, right? Because this is all the stuff that's greater, and this way is all the stuff that's less. Now, if I were to graph x is greater than or equal to 7 on the same number line, I would say, ooh, well, x is greater than or equal to 7. Here's 7. If we're greater than or equal to that, I'm going to shade that in. And I'm going to shade everything to the right. That would cross over this value of 10, which would essentially shade in the circle for us, right? It includes that value of 10 now because that would be included in here, right? 10 would be greater than or equal to 7. So this second inequality is almost redundant. It's almost repetitive. It doesn't really add anything to the mix. This includes more stuff than this one, right? This overlaps this. So our solution, yes, while technically x is greater than or equal to greater than or equal to 7 or x is greater than 10, really only this one is reflected in the graph because this is just more inclusive than this. Does that make sense? So this kind of overrides this problem, and really our solution just boils down to this one. In the previous examples, our solution would definitely have to include both components because both components are reflected in the graph. Do you see that? Both components are reflected in the graph. Both components here, I'd have to kind of write it a little on the same line, are reflected in the graph. But up here, one of these components kind of overrides the other, right? It just like overlaps it. It takes it over. This is just superior than this in terms of the fact that it encompasses more stuff. It includes more things. All right. Hopefully that makes sense. Let's take a look at another one in which that's the case. So it is possible to have both of your inequalities pointing in the same direction. And when that happens, it's essentially a matter of figuring out which inequality just sort of dominates the graph and takes over. All right. Take a look at something like this. We have negative 7 minus 6x is greater than negative 4x minus 9. I like that problem. It's a lot of negatives. Or 9x minus 4 is greater than 6 plus 10x. Okay, consider an inequality kind of like that. Again, I'm going to solve both of them separately and then see how my solutions look on a number line. All right. What I would do here is I would, let's see, get all the variables on one side. So add 6x. Get rid of the minus 6x. Gives us negative 7 is greater than negative 4 plus 6x is 2x minus 9. Again, you certainly could add 4x and add 4x, but it does keep everything positive, which is kind of nice. I would add 9 to both sides now to get x alone. We have a two-step inequality. Even though the x is on the right side, we're still just trying to get it alone. Add 9 gives us 2 is greater than 2x. Now we have 2 times x. I want to eliminate that multiplication by 2. I'll divide both sides by 2 and get that 1 is greater than x. Okay. Of course, we've seen in the problems we've done already that we can rewrite something like 1 is greater than x, if we read it from right to left instead, as x is less than 1. So if you feel comfortable taking this and rewriting it to get x on the left side, you certainly can. If you're comfortable with this, then absolutely you can leave that alone. But if you want that x on the left, you can just rewrite it. Okay. Let's solve the other one. So we have one potential solution set of x being all the numbers less than 1. Let's try this one as well. Let us first, I'd probably subtract the 9x, right, to keep everything positive. We get negative 4 is greater than 6 plus 1x, right? 10x minus 9x is just 1x left over. Now to get that 1x by itself, I would subtract 6 from both sides, and we get that negative 10 is greater than x. And again, if you prefer to switch things around and rewrite it, you could write this as, reading from right to left, x is less than negative 10. X is less than negative 10. Okay, if you want to leave it like that, totally fine. All right. So think of our answers that we get here. We get x is less than negative 10, and also x would be less than 1. Well, x is less than 1 includes more stuff than this does, right? This is just a subsection of this. It's just a subset, right? It's just a part, a piece of what this includes. Because if I express both of these on the graph, right? Here's 1. Say 1 is way over here. Here's 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, 9, negative 10. Right here, negative 10. Extend that a little further. Right? If I'm including all of the values less than 1, well, we're going to have an open circle here, and we're going to be shading everything to the left all the way less than 1. And if you notice, that's just going to include all of this stuff less than 10, right? Here, normally, to graph x is less than 10, I'd have an open circle, and I'd be shading everything over here, right, to normally graph x is less than 10, negative 10. But this graph of x is less than 1 is just going to completely overlap and take that over, right? It's just going to completely overlap it and dominate that graph. And so our solution here is really just that x is less than 1. Because saying that x is less than 1 or x is less than negative 10, well, negative 10 is already less than negative 1. So it's redundant. It's not necessary to have this second condition. Hopefully that makes sense. It's a little bit of logical thinking. You're thinking to yourself, like, why do I need to even say this? If I already have this, this is just more things. So that's good. We want more things. This is just restricting me further. I don't want to do that. Okay, that's one way to kind of think about it. Notice we do have the open circle as well. If you graph these in reverse, say you graph this one first, that's totally fine. You would say x is less than 10. You'd have an open circle, shade everything to the left. And then this one, you'd have an open circle, shade everything to the left, and you notice your graph would just eventually overlap this value, making it unnecessary. This would be the one we need. All right. So what we've seen so far, just to do a quick recap, we've seen problems where both your inequalities are completely disjointed. They're completely separate, where they're just going in opposite directions. They don't interact with each other, and we just put both of them on the graph. Those, I think, are not so bad. These can get a little confusing because it's up to you to determine which part of the graph are we really focused on. Are we really focused on this? Well, not really, because this just includes more things. Are we really focused on this? No, we don't really need to specify that because it's already contained within this group of numbers. All right. What happens, though, ask yourself this. What happens when we have both inequalities going in opposite directions, but they happen to crisscross each other? Let's think about it. Consider something like this. Ready? Let's do 7 plus 4x is greater than 3x minus 4. Or 7x plus 6 is greater than or equal to 9x plus 2. All right. Variables on both sides, but it's not going to stop us. What I would do is I would subtract 3x here on both sides to eliminate the plus 3x. I'd have 7 plus 4x minus 3x, 1x, is greater than negative 4. Now I would subtract 7 from both sides to get the x alone, and I get that x is greater than negative 11. That's negative 4. Take away negative 7. So that's a pretty good start, right? X is greater than negative 11. Cool. We know how to graph that. We're good with that. This one over here, I would, just to get the variable on the left, I'll try subtracting 9x this time. Gives us negative 2x plus 6 is greater than or equal to 2. Now we have a two-step inequality, which we love. To get that x by itself, we need to get rid of everything else on that same side of the inequality. Subtract 6 first. We get negative 2x is greater than or equal to 2 minus 6, negative 4. Divide both sides by negative 2 to undo that multiplication of negative 2 times x. Of course, we're dividing by a negative, so that's going to flip-flop that inequality, giving me x is less than or equal to 2. So take a look. So not so bad, right? We have this and this. But now take a look at what these graphs are going to look like. Here's my graph. I'm going to try to stretch it out so I can really make it accurate here. Suppose that this is my value of 2. Right? If that's my value of 2, we'd have 1, 0, -1, -2, -3, -4, -5, -6, -7, -8, -9, -10, -11. You don't have to make your graphs super accurate like I am right now, but I'm just doing that to try to explain it to you clearly and give you a clear demonstration. But if you want to, you don't have to scale your graphs out like that. You should try to make them somewhat accurate. Like 2 and a -11 are pretty far apart, so they shouldn't be like squished right next to each other. But again, you don't have to like actually scale them out like that. I'm not going to require you to do that. All right. But let's see what this is going to look like. Well, x is less than or equal to -2. We would have a closed circle here, and we'd be shading everything to the left of -2. All right, go on like that forever. Okay? But take a look at this graph. X is greater than -11. Well, that would mean we'd have an open circle, which, by the way, kind of gets filled in by this shading of x is less than or equal to 2, and we'd shade everything to the right. So when all is said and done, we have shading occurring to the left forever and shading occurring to the right forever, and everything in between is also captured in that. Unlike these, notice, where we had this gap in between, here, now everything in between is captured by this shading. And so since we're going forever to the left, forever to the right, and we include everything in between, not surprisingly, our answer here we would say is all real numbers. Okay? So when dealing with compound inequalities with the word or, it is possible to get a solution of all real numbers if your inequalities happen to go in opposite directions and they overlap. Because then you'll be shading forever this way, shading forever this way, and you'll include all of that overlap in the middle. So it's literally the whole number line. All right? Hopefully that was a pretty good explanation. We saw some problems that were just straight up disjointed problems where it's just one arrow one way, one arrow the other way. We saw a couple problems that happened to overlap, and we had to think about which one of these two conditions would sort of dominate the graph and include more stuff, because this kind of just takes over here. You see that this graph just takes over the other one. And then we saw a problem where it was actually a solution of all real numbers because the graph shaded in both directions and overlapped each other. All right? So hopefully this was a good explanation on compound inequalities with ORs. We'll be sure to practice this more in class, but I do recommend practicing the problems on Google Classroom. The answers are provided as well, so give those a try. All right? Thank you so much for your attention and focus today. I hope you have a great day and look forward tomorrow to compound inequalities with AND. Take care, everyone.